Microsoft just built the world's first computer that doesn't run on electricity. It runs on light. It's 100 times more energy efficient than GPUs, it already runs real AI workloads, and it just solved financial and healthcare problems faster than quantum computers struggle with. No fans, no overheating, no silicon limits, just pure optical speed. So let's break it down. Microsoft calls it an analog optical computer, the AOC. In plain English, it's a light-powered computer that works where normal chips fail. So how does it work? The AOC doesn't process information like a digital chip does. It doesn't flip ones and zeros. It literally shines beams of light through modulator arrays and reads the output using smartphone-style camera sensors. The light intensity itself encodes the data. You add and multiply using light. The core of this machine uses micro LEDs, spatial light modulators, optical lenses, and photodetectors. Instead of running code line by line, the AOC loops a problem over and over, improving the solution with every pass until it reaches something called a steady state.
Outputs are then fed back to the optical source, and I'm repeating this till the system converges, till I found which stock I should invest on. And there are really three aspects of this architecture that are very important, and I hope you can take home today. The first one is that this is a truly analog machine. The signals are remaining in the analog domain till the solution is spit out. Second, as opposite to Neumann's architecture, there is no separation between compute and memory. The signals are propagating through the solver as I do my computations.
That's the final answer. And it's not just an academic toy. The researchers ran this system on real optimization problems, ones you find in banking and MRI scanning. In the finance demo, they tackled something called a delivery versus payment problem. This is the kind of algorithm clearinghouses run every day to settle massive batches of financial transactions between banks. Barclays partnered with Microsoft for this part. The test involved 1,800 parties and 28,000 transactions. Just one small batch, sure, but the results were clear. The AOC hit a much higher success rate than quantum computers attempting similar problems. Now the coolest part? They've got a digital twin, a software model that mirrors how the physical AOC works. This twin lets them simulate what a future AOC with millions or even billions of variables would do. And yes, those scale-ups are already planned. They're building better versions every 2 years. The vision is crystal clear. Eventually, this machine could handle transaction loads across entire clearinghouses, potentially reshaping global banking infrastructure. And it's not just finance. The healthcare use case is just as compelling. They used the AOC to reconstruct a full MRI brain scan with only 62.5% of the original data. Normally, a high-resolution MRI can take 30 minutes, but with this kind of compressed sensing optimization, the team believes they can get it down to 5. That's not just speed for speed's sake. It means more patients scanned per day, lower operational costs, and possibly faster diagnoses. The prototype isn't ready for hospitals yet, but the digital twin simulations show it can scale to medical-grade tasks. And yes, the AOC can already handle AI workloads. This isn't just about optimization anymore, it's about inference. The team figured out how to map deep equilibrium models onto the AOC. These are AI models that work by finding fixed points, kind of like reaching a mental conclusion by constantly adjusting your thought process. You feed it input, it loops through internal calculations, and it stops when it finds the best output. The AOC was practically made for this kind of work. Instead of just pushing data through layers like a normal neural net, it recycles and updates that data inside a feedback loop, an exact match to how the hardware behaves. Yanis Gladro, an AI researcher on the team, explained that these equilibrium models could handle things like state tracking. That's the ability to remember and update internal thoughts or decisions based on what's happening around you. A must-have for humanoid robots trying to navigate the world or have meaningful dialogue. That's one of the biggest bottlenecks in today's AI systems. GPUs struggle with, but the AOC, it might do it faster, with less energy, and without burning through power like a data center furnace. Now, the current hardware is still pretty small. It runs about 256 weights, but they've already demonstrated time multiplexing. That means instead of needing bigger hardware, you can run smaller pieces of the model sequentially and stitch the results together. They even trained a 4,096 weight ensemble model this way, and it worked. The AOC classified MNIST and fashion MNIST images with accuracy nearly identical to their digital simulations. No calibration tricks, no extra tuning, just raw analog computation. Let's talk hardware details for a second, because this thing is a wild mix of components. The matrix vector multiplication is done optically. Micro LEDs emit light encoded with data. That light passes through spatial light modulators, basically pixelated filters that control how much light gets through, and hits photodetectors that turn it back into electrical signals. From there, the analog electronics take over, applying nonlinear transformation, subtraction, addition, annealing, all that math, before looping the signal back around. It's a hybrid system, but there's no digital conversion in the middle. That's the key. The analog signal stays analog the entire time, which is what keeps energy usage low and processing speed high. What about scaling? Well, each component, micro LEDs, sensors, modulators, is already built using supply chains for consumer electronics, so this isn't one of those moonshot projects that needs custom chips or rare materials. The Microsoft team believes they can scale the architecture using modular optical blocks, each with its own micro LED array, SLM, and detector. By stacking these modules into a three-dimensional mesh, they could hit 100 million weights, or even 2 billion. Within realistic manufacturing limits, and because micro LEDs are incoherent light sources, you don't need perfect alignment like you would with lasers. That's a massive win for manufacturability. Even the performance numbers are wild. They're projecting 500 tera operations per second per watt. To put that in perspective, high-end GPUs today struggle to reach 5 tera ops per watt. That's not a small leap. That's 2 orders of magnitude. And at just 8-bit precision, this machine could blaze through AI inference or optimization tasks while sipping power like a smartphone charger. Oh, and about the algorithms. They didn't just build the hardware and throw it at random problems. They developed a new kind of optimization formulation called QMO, quadratic, unconstrained mixed optimization. It handles both continuous and binary variables. That's useful because most real-world problems aren't clean-cut yes or no decisions. You need shades of gray. They solve QMO problems for MRI reconstruction, financial settlements, and nonlinear regression, all on the same hardware. And unlike traditional QMO formulations that require dozens of extra variables to model constraints, QMO can represent those constraints with just a few added dimensions. That's what makes it practical. For the MRI reconstruction, they implemented compressed sensing using a version of QUMO. They took a Shep-Logan phantom image, removed 37.5% of the data, and used the AOC to fill in the gaps. The result? A mean squared error of 0.008 using only 64 variables. When they scaled it up with the digital twin to over 200,000 variables for a real brain scan, the results held up. That opens the door to medical imaging applications that are faster, cheaper, and less stressful for patients. And then there's the financial test. This wasn't toy math, it was a scaled-down model of real-world security settlement, built with Barclays. They fed the AOC a dense, multivariable problem with constraints, penalties, and competing priorities. The hardware nailed it. Not just fast, but correct. In contrast, quantum computers running similar benchmarks get it right only about half the time. And this is more than just another weird experimental computer. Microsoft's Analog Optical Computer isn't replacing your phone or laptop anytime soon. But for AI reasoning, for optimization, for massive compute loads that humanoid robots or complex simulations will need, it's an entirely new path forward, one that might just be necessary to keep this whole AI boom from running out of energy, literally. That's it for now. See you in the next one.